Greetings. So, this is the paper in which Schrodinger discussed entanglement in 1935, and there are concerns about it because this was the first time that physicists had to deal with counterintuitive ideas. Not that these ideas are wrong, this is the correct description of nature as it turns out, but when these ideas were introduced, and it's like a long time now, and it seemed so unusual that there were many concerns raised about it, and mostly by Albert Einstein. We discussed his objections in the previous class. And Einstein, Podolsky, Rosen, their conjecture was that, okay, if two particles can be entangled regardless of the distance between them, instantly, because information is known not to be communicated at superlight speeds or superluminal speeds, then they are carrying some information. There is some medium which is available to them to carry this information, which is there in the hidden variables. And this led to huge debate between Einstein and Bohr, which eventually Bohr seems to have won. And the counter ideas are really shocking. We have been discussing these, but every time you address this issue, it seems to be very strange, like the sequential Stern-Gilroy experiment, which we have discussed in our previous classes, that you have these silver atoms which go through the Stern-Gilroy apparatus, and you have got a magnetic field along the z axis, and you block those atoms which have got spin down. It has got one electron on the outer side, and that has got half integer spin, which can be oriented either along the direction of the field or opposite to that, and you transmit only one component, which is the plus component or the spin up component, and you send it through another Stern-Gilroy apparatus which has got a magnetic field in the same direction as the previous Stern-Gilroy apparatus, then it goes through. But then the second Stern-Gilroy apparatus, if you turn it through 90 degrees, then two components emerge, not one. Okay? And if you do put a third Stern-Gilroy apparatus and you block one of those, and now once again you have a Stern-Gilroy apparatus which has got the magnetic field along the direction in which you had the first Stern-Gilroy apparatus field, then both the components emerge, which is really strange, because if you see in the lowermost diagram, the Sz minus is blocked, but what comes at the end, the Sz minus reappears. So, it is like putting apples and oranges together and then remove all the apples, and then after some time you rediscover them. So from the classical point of view, this idea is very strange. So, this was the consequence of the principle of superposition, and we do not have to worry too much about a photon bursting into an electron or positron. You can have anything, any singlet pair, okay, which breaks up into two fragments. It can be an eta meson which bursts into a mu plus and a mu minus meson, all right, or it can be some molecule in an excited state, or for that matter even an atom in an excited state. So, all of these excited states are essentially resonances. The reason they are there is because the Hamiltonian for the system has got an eigenspectrum which Saurav knows very well. So, you have bound excited states which may overlap with a continuum, okay? And then there is a certain probability of being either in the bound state or in the continuum state, and the one in the continuum state, if it decays, then you are going to have two fragments. And then you will have two particles going in opposite direction, and you can then measure their components of the angular momentum, the magnetic moment which is proportional to the angular momentum, right. And you can measure this. For spin half particles, it will be either up or down. So, you have got plus half and minus half states for the particle 2, and similarly plus half and minus half in units of h cross for the particle 1, right. So, this is the fragmentation that can take place. So, we are going to consider such a fragmentation to set up some elementary ideas about the probabilities, and which will give you a measure of correlations, and then ask ourselves, is this correlation that we get from quantum mechanics, is it compatible with the correlation you can get from classical physics? Because classical physics also definitely leads you to probabilistic considerations depending on what information is concealed from you by hidden variables. So, it can give you some correlations, some probabilistic correlations, whether these are compatible with the predictions of quantum mechanics, not just predictions, but measurements, because you carry out experiments in your labs and then find out what is it that you see and what are your results compatible with. So, are they compatible with correlations that you can get from a hidden variable theory? So, that is the question we are going to ask. So, the product state of the two atom system will be constructed from the product of individual atomic states, the fragment states. So, it will be the product, and it will be a properly antisymmetric product because you are dealing with fermions. So, the possibility of having a plus sign in between is ruled out, okay. So, that you have a fermion state. If you interchange the particles, the sign of the wave function will change, right. And you convince yourself that this is the right fermion product state for the two particle system, and this is the state that we are going to work with. Now, you can carry out these measurements using Stern-Gulrack apparatus, and the distance between them can be huge. It can be from anything from few meters to kilometers to light years, all right. It does not matter, because our arguments are not going to depend on the distance between this. So, you have huge distances between these magnets, magnetic fields, all right, and you can also set up the magnetic fields in different directions. Means you have one apparatus here and the other apparatus here. This can be oriented with magnetic field along this axis, but you can also turn it, and you can also do the same with this. You can have the magnetic field like this, or you can turn it through any angle, theta 1, theta 2, right, 45 degrees, 90 degrees, why not, anything, right. So, they can be oriented differently, and notice that these angles theta 1 and theta 2 do not really have to be equal, okay. They may be equal in some situation, but they may not be, they do not have to be. So, that is the experimental setup that we have in mind, and if you have a different orientation, which is at angle theta 1 with respect to your first reference orientation scheme. So, this is your original coordinate system, and you are going to talk about orientations with respect to this coordinate system, and the one on which is going to measure the spin components of particle 1 is inclined at an angle theta 1. So, this is the unit vector along which it is inclined, which is Ez prime, and here this is Ez double primed for the particle 2, which is inclined at an angle theta 2, which may be different from theta 1. Okay, so, that is the setup we have in mind. Okay. We do have to worry about this. Is Ez prime the same as Ez double prime? Is the angle theta 1 exactly the same as theta 2? It may be or it may not be, and the experiments are done by 2 observers, and for some reason they are always Alice and Bob. I mean, I think I read somewhere, but now I have lost that reference. It was somebody who first used Alice and Bob, and since then everybody has used Alice and Bob. Okay, but it can be any 2 of you if you like. All right. So, the experiments do not depend on the observers being Alice and Bob, but for some reason they always are. So, Alice and Bob carry out these measurements. Okay. Alice is going to carry out her measurements on particle 1, Bob on particle 2. They can set up their apparatus so that the magnetic fields in their apparatus is parallel to each other along the original Ez direction, which is shown in the green apparatus at the top. Okay. But they may use a different apparatus which is oriented, which is turned with respect to the previous one at some angle, which I have colored as blue. Okay. But then it can be oriented at some other angle as well, which is colored red. Okay. So, red and pink are all approximations of each other, so that works. All right. So, do not expect to find a color which is exactly which my wife would have when she wants to buy a sari. Okay. It has to be exact the same shade. So, that is not our concern here. So, here you have Alice and Bob carrying out these measurements, okay, and they can pick any apparatus. They can pick either an apparatus whose magnetic field is oriented along the green field or the blue field or the red field. Okay. The fields do not have colors, but you know what I mean. It is the orientations. So, these orientations in our tentative vocabulary, there is a one-to-one mapping between these orientations and the colors, okay, because I am going to use this color analogy later, and that is the reason I want to start building in this association from right now. Okay. So, these are 3 different orientations. The color of the apparatus of course does not matter, except that it is an association that we are going to refer to later. So, let us say you have got a diatomic molecule or something which is going to explode into 2 pieces, right, and then you have got eigenvalue equations for particle 1 and for particle 2, right. This is superscript 2, it is not the square of this, right. But then of course, there is the square of the angular momentum to which this commutes, which is what gives you the spin half quantum number. So, both are spin half quantum numbers, all right. So, now how do you write the product state? Here you have written the product state in terms of the wave functions of particle 1 and particle 2, and you construct an antisymmetric combination. And here for the rotated apparatus, once you have this apparatus rotated and this apparatus also rotated, it would be tempting to construct a similar product wave function by simply putting single prime on this. So, you have phi 1 over here. So, you put a phi 1 prime over here and you have phi 2. So, replace phi 2 by phi 2 double prime and do the same with these two terms, and it would be tempting to simply put a prime and a double prime and hope that this would be an appropriate antisymmetric wave function. Now, this will work if and only if theta 1 is equal to theta 2, not otherwise, and you are going to see this more clearly as we discuss this further, but it is not true in general. You cannot just put a prime and a double prime and get the corresponding wave function, and we are going to construct this wave function systematically. All right. So, you cannot simply put prime and double prime and get the product state with reference to the rotated apparatus. So, this is the first thing I want to drive home. Okay. If theta 1 is equal to theta 2, you can do that, but not otherwise. So, if theta 1 is equal to theta 2, you can just put a prime on this and a double prime on this and get the product state, not otherwise. So, basically let us construct the direct product states of the two atomic spins. So, that is what we are going to do now. We will build that product state, and we build it using a basis set, and we have three sets of basis sets which are available. First is the original one with reference to the first magnetic field, which is here in the upper left corner, right. So, you have got a basis set of eigenstates of Sz, which is phi 2 plus or minus. Similarly, you have got eigenstates of the one tilted at theta 1 and another basis set coming from those eigenstates with reference to the field which is tilted with respect to the original field at an angle theta 2. Okay. So, your axis of quantization, so there is no sacred space, sacred direction in space, but we have considered the original direction Ez as our reference. Okay. And with reference to this, so this was the axis of quantization for the first apparatus, and with reference to this you can change the axis of quantization, and there are two options over here. So, together we have these three basis sets, each is a complete set of bases. We have these three eigenvalue equations, and you can express any base vector of any one as a superposition of base vectors of the other two, okay, as long as you have a linearly independent complete basis, and the completeness requires only two of these states. So, this is a discrete basis, just two dimensional basis, and you can express any one as a linear superposition of the other two. So, that is what we will do now. So, you have got an eigenbasis over here which is phi 1 plus prime and phi 1 minus prime. So, these correspond to the spin up and spin down. Okay. This is up and this is down, with a single prime corresponding to the angle theta 1 for the particle 1, and this is another eigenbasis set for spin up and spin down for the particle 2, which is the double primed phi's. Okay. So, these are the alternative basis sets which are available to you, and using these two alternative basis sets, you can write phi 1 plus and phi 1 minus as a linear superposition of phi 1 plus prime and phi 1 minus prime, okay, because it is a complete basis, and you can do the same for the spin down component. So, what is the basis used is phi 1 prime and phi 1 minus prime, and here it is this eigenbasis, and you have expressed phi 2 plus and phi 2 minus in this basis. Fair enough? So, it is just writing an arbitrary state as a linear superposition of a complete set of bases. There is no more mysterious than writing a vector in one basis or a rotated basis. Okay, it is just the same. So, you have these basis sets, and having done that, you just make sure that you have done it correctly. So, you can verify the orthogonality of phi 1 plus and phi 1 minus when they are decomposed in the basis sets. So, go ahead and construct their overlap, okay? And you know that phi 1 plus prime is orthogonal to phi 1 minus prime, right. So, you construct these overlap integrals and you can see that it vanishes, okay. All the terms go to 0. So, it is very straightforward to do that. You also verify that these are normalized. We begin with a normalized eigenbasis, so that the normalization is preserved through unitary transformations, and you construct the normalization integral, which is the overlap of phi 2 plus with itself, right, and you can see from the orthogonality of phi 2 plus and phi 2 minus that this overlap integral goes to 1. So, they remain normalized. So, everything works out fine for phi 2 plus, which is the up state, and the same thing can be verified easily for the down state, okay, using the same overlap this thing. So, everything is working out all right. So, this is our direct product states of the two atomic spins, which is the product of phi 1 plus and phi 2 minus phi 1 minus phi 2 plus. So, that you have an antisymmetric state. Remember that it is the rotation through 4 pi which give us the unit operator, and not rotation through 2 pi, because we are dealing with half integer spins. We discussed this yesterday and we are going to depend heavily on this idea today. So, you have therefore chosen these coefficients to be cosine theta 1 by 2 and sine of theta 1 by 2. So, you know that cos square theta plus sine square theta is always unity no matter what the angle is, okay. And this angle would be for a normalized state, you can write the coefficients therefore as cosine theta and sine theta. They can come with either plus or minus sign, it does not matter depending on what kind of a combination it is, symmetric or antisymmetric, right. But the coefficients can always be written in a two state vector as cosine theta and sine theta. But with reference to the angle theta 1, I have chosen this coefficient to be cosine of theta 1 divided by 2 and not theta 1 itself, okay. So, the normalization can be explained using any damn angle, it does not matter. But I have chosen this to be theta 1 by 2 because we discussed yesterday that when we are dealing with half integer spin particles, it is a rotation not through 2 pi which gives you the unit operator, but at a rotation through 4 pi. So, all considerations with respect to the angles need to be dropped to angle divided by 2. So, we have chosen these coefficients to be theta 1 by 2, cosine of that and sine of that, and you have two possibilities over here, one which is antisymmetric and the other which is symmetric, and both are fine. One will give you the spin up state, the other will give you the spin down state. Both are normalized, okay. The sum of the squares go to unity, right, and we can do this in terms of the phi 2 double prime basis. We have done it in the phi 1 single prime basis, but we can also do it in the phi 2 double prime basis, okay. In which case the angles would be theta 2 by 2 rather than theta 1 by 2, okay. So, good. And now let us write this product state. So, you have got a product of phi 1 plus, phi 2 minus, phi 1 minus, phi 2 plus. So, you construct it from these decompositions in the two alternative basis sets. One is a prime basis set and the other is a double prime basis set. So, it is really very simple, but it has to be done thoughtfully, okay. So, I have written this product wave function now in terms of these decompositions which we have. So, there is one decomposition in the phi 1 single prime basis and the other in the phi 2 double prime basis. And then you have got the first factor, which is this red, which I have written in this red as a decomposed in these two components. Then I have got the second component, which is phi 2 minus, which is here. Then I have got a phi 1 minus over here, which is the blue, which comes from here, phi 1 minus, and that is sitting over here in this beautiful bracket. And then the last one is phi 2 plus, which is coming from here, and that comes over here. So, it is very straightforward, simple, but very easy to make a careless mistake and forget 1 prime, put 2 primes instead of 1, and then worry about it for the next 1 hour. Okay? So, do it carefully. It is very simple. Got it? Okay. So, let me bring this equation which is in which the product states are decomposed at the top of the next slide. Okay? And now, I have to multiply these vectors with these. Okay? So, I have to multiply this vector with this, then this vector with this, and construct these direct product states. So, these are sometimes called even as tensor product states. These are the direct product states that I have to construct. Okay? And to be able to keep track of terms, because there will be several terms coming out of it, I am going to number these factors. Okay? So, I will number these as 1, 2, 3, 4, 5, 6, 7 and 8, and the first product will be that of 1 and 3. Okay? And then I have 1 and 4, then 2 and 3 and 2 and 4, and I have to keep track of the sign, because there is a minus sign here, there is a minus sign here, there is another minus sign here. So, make sure that all the signs are taken care of. And then I have the product from 1 and 3, which comes here, which is cos theta 1 by 2, cos theta 2 by 2, and the direct product of these two vectors, which is phi 1 prime plus and phi 2 minus double prime, which comes over here. Okay? So, that way I have constructed all the products 1 3 1 4, then 2 3 2 4, 5 7 5 8 and 6 7 6 8. Got it? So, you have got these 8 terms which you get, right? Okay. So, let me, but you have to do it carefully, you have to do it yourself. So, we bring this result to the top of the next slide, and now recognize that there are some direct product states which are common. For example, these two which are underlined in red, they have the same direct product states. They have phi 1 prime, phi 2 double prime minus, which is the spin down, all right, in both the terms, and you can combine them, and then you can use trigonometric identities to write the corresponding coefficient. Okay? You can do the same with these two. Okay? They have got the same factors. Then you have another pair of 2 terms and also the last one. So, in each case you can combine the terms, isolate the common factors and use trigonometric identities for the difference angle, the cosine and the sine of the difference angles, all right. These are the common trigonometric identities which you have been using in your high school, right, and then rewrite this in a simplified form, which is this. So, now you have got this sine and the cosine of the difference angle. So, theta 1 and theta 2 may or may not be the same. If they are the same, then theta 1 by 2 will cancel theta 2 by 2, right, and then you will get a cosine of 0 for the first term, which will give you unity, whereas the sine term will vanish, okay, because the sine of 0 will go to 0 even in quantum mechanics, right. So, here you are. So, this is what you get after using this trigonometric identity. Okay, you get the logic, means I do not want to do it step by step, but I will just run you through the logical scheme. And I have just rewritten it to have the cosine terms at the top and the sine terms at the bottom. Okay, there is nothing new in the middle equation. And as you can see, if theta 1 is equal to theta 2, then you could have placed just the prime and the double primed as we had seen earlier, but not otherwise. Okay, this is what I had mentioned earlier. So, if theta 1 is equal to theta 2, you are fine, but not otherwise. So, this is the result that you get. And now we ask, what is the probability, and listen to this and read this question very carefully. So, you got two Stern-Gilbert apparatus, one which will measure the spin component of particle 1 and the other which will measure the spin component of particle 2. What is the probability that the apparatus measures for atom 1, for particle 1, to have the spin up state and simultaneously measure the spin component of the particle 2 to be also in the up state? Okay. And this is the question which is going to give you some measure of correlation. And then we are going to ask, is this correlation explicable in terms of hidden variables? We also know how this correlation is explained using quantum mechanics, and are these correlations consistent with each other? And that will give us a test of whether a counterfactual theory which has got local hidden variables gives you an appropriate description of nature. Okay, so, that is a test that we want to carry out, and you can do this because once you get spin up or spin down, you can have another Stern-Gilbert apparatus after that, which has got a magnetic field completely parallel to the previous one, and then check out, because we know that a system which collapses into an eigenstate remains in that eigenstate. So, any time you measure it, you will always have the same component, right. So, you can perform sequential Stern-Gilbert measurements to ensure that, okay, you are talking about the spin up or spin down. Okay, because the system on which a measurement has been carried out collapses into an eigenstate, and it will remain in that eigenstate unless you put it through some other Stern-Gilbert apparatus which is orthogonal to the previous one, so that you can regenerate the superposition. Okay. So, you can test this out very easily, and this is the question that you are addressing. And you have these different eigenbasis states. The prime is written weirdly on the left because it could be the theta 1 or theta 2 or a theta 3 or whatever. Okay. So, there are it is only to remind us that it depends on the angle. So, this is the product state now that we have got. And notice that the first term has got spin up and spin down combination, okay, particle 1 in spin up and particle 2 in spin down. The second term has got a down up combination, the third is up up, and the fourth is down down. Okay. So, these are the combinations that you have got. What is the probability that the product state will be in a down up state? Particle 1 in down state and particle 2 in up state. What is that probability? It will be the square of this coefficient, right, for the down up. Okay, so we know that from quantum mechanics. Okay, that when you write a wave function as a superposition of various terms, then the coefficients give you the probability amplitude and their modulus square. These are in general complex numbers. Here these are real, but they are with plus and minus signs, but when you take the modulus square, the sign does not matter. Okay. And quantum mechanics tells you how to find this, the probability of the down up state or the up down state or the up up state or the down down state, right. So, this is something that you are going to get from quantum mechanics from the modulus squares. So, this is the modulus square, and the probability for the up state is half of sine square theta 1 minus theta 2, all right. And notice that this will go to 0, okay, which it should, and then you have the up down and down up probabilities which come from the cosine square terms. So, these probabilities we interpret in terms of quantum mechanics. They are coming from the principle of superposition, they are coming from this idea of entanglement, that a wave function a system is not always in state 1 or state 2, but it is in a superposition of both the states, and you do not know in which state it is unless you carry out a measurement. And once you carry out the measurement, the system would collapse into an eigenstate, and then it will stay in that until something happens to the system to regenerate the superposition. Okay, so that is the fundamental understanding, fundamental interpretation of probabilities in quantum mechanics. And Alice and Bob, they will carry out their measurements, they will find out if it is up or down and find out what is the correlation between their observations. And these correlations, they will ask if these are accounted for by quantum mechanics or can they be accounted for by hidden variables. And how to account for these probabilities, how to account for these correlations using hidden variables is something that I am about to discuss either in this class or in the next class. But we will first conclude this, that if you have, for example, now we know that the coefficients depend on the square of the sines and cosines of what angles? Half the difference angle. Okay. So, if the difference angle is 45 degrees, half the difference angle will be 22.5, and then you know what is the sine of 22.5, what is its sine square, and this sine square term is what will give you the probability, right. So, you can examine the up state. If the difference angle is not 45 degrees, but it is 90 degrees, then you will have the difference angle to be 90 degrees, half the difference angle is 45 degrees, and then you get the sine and the sine square, which will be half. Okay. So, these are the probabilities that you expect for the up combination from quantum mechanics. Okay. And these correlations, the quantum correlations, impact the probability distribution, right. So, what if in quantum mechanics we know that there is entanglement, okay. That is what we are trying to account for. So, if both are oriented exactly the same way, then we know for sure that if one is up, this is plus half, this must be minus half. Okay. If this is plus half, this must be minus half, pointing downward. If this is up, this must be down, and vice versa. all right. It would be the same if both are tilted at the same angle. So, if this is up, this would be down. Okay. So, in the bottom equation you have got the m1 which is equal to minus m2, and the subscripts z, z prime, z double prime are to be read in correspondence with each other. If you have a z on the left, you have got a z on the right. If you have got a z prime on the left and a z prime on the right, then one is exactly the opposite of the other according to quantum correlations. But if one is z and the other is not z, it is z prime or z double prime, then it does not have to be. Then there is going to be some statistical correlation between whether it will be up, up or up, down, and that will be given by these relations where the difference in the half the difference of those angles will give you the probabilities of the up, up or up, down and down, down and up, up combinations, right. Got it? Good. So, this is what we have got, and in classical probability, when you toss a coin, and I had the choice of choosing either a 1 rupee coin or a 100 rupees coin, so why not a 100 rupees, all right. So, here you can get the either side reverse or obverse, okay, and the probability is half, not because of any quantum considerations, but because when you flip the coin, all right, you do not know the exact torque that you are applying on the coin, you do not know what forces are there. So, you do not know how high it will pop up, you do not know whether it is going to land on the table or on the floor, and in between what it is going to interact with. There are different molecules of airs, and you do not have this information. This is the information which is hidden from you, and you therefore cannot predict how the coin will land. So, there is an uncertainty, but this is not quantum uncertainty. This is classical uncertainty coming from information which is hidden from you. This is the local hidden variable account for uncertainty. And the question that we are dealing with is the quantum uncertainty, can it be accounted for some sort of hidden information. Okay? So, this is the big debate between Bohr and Einstein that we discussed in our previous classes. Or is entanglement intrinsic to nature as Bohr had claimed. Okay? So, we are now going to think of experiments done by Bob and Alice on particle 1 and particle 2, okay, using their own apparatus, and they can have a magnetic field which is both aligned like this, or one aligned like this and the other at one angle or a different angle, right. The angles may or may not be the same, and that is going to determine the difference angles, the half the difference angle, theta 1 by 2 minus theta 2 by 2 is what we saw, and those are the ones which will give you the quantum probabilities. So, are these quantum probabilities compatible with correlations that you can get from hidden variables? So, you have to, we are now going to discuss in the next class what would be the prediction of hidden variables. You do expect some correlations. Okay. There is some chance, when you toss a coin, there is some chance that it will be either obverse or reverse, and there will be some correlation. Now, what is a measure of this correlation, and can we account for this correlation using classical ideas, and that is something that we will discuss, and then ask if these results are compatible with what we get from quantum mechanics. What is it that we get from quantum mechanics? These are given by the coefficients of those up and up down terms. Okay? So, they come as sine and cosine, and their modulus squares give us the probabilities. So, that is what we will discuss. Most of the discussion that I am presenting to you is from this paper by David Harrison in American Journal of Physics. It is a nice paper, so you will enjoy reading it. And in our next class, we will compare measures of correlation from local hidden variables and compare it with measures of correlation from quantum mechanics. Okay? And what we are going to find is that there are certain inequalities which must be satisfied if they are accountable by local hidden variables. And if that inequality is broken, then it would mean that quantum theory has a completely different intrinsic nature of entanglement. Thank you. Any question?
In the case of direct product of particle 1 and 2,
Yeah.
We are using the terminology like direct product, correlation and entanglement, all terms are similar
No.
in this special case.
Yeah, what you're dealing with is constructing the composite wave function,
Okay.
which is a direct product of the two, and their coefficients will have information about the entanglement, because it is in the same space. So, what we are saying is that the interaction which leads to the two particle system is not so strong that you are thrown out of the Hilbert space. You remain in the same Hilbert space, and therefore, any state is represented as a superposition of the basis set that you had to begin with, right. So, that is coming from the product states, from the eigenbasis of both. Any one can be used to expand an arbitrary wave function, because it gives you a complete set of bases, and that remains a complete set of bases for the product states. So, the only contention over here is that you are not thrown out of the Hilbert space, and therefore, you can write the wave functions as product states. And the measure of entanglement is then contained in the coefficients. Okay, they will give you the probability of both the particles being up or both the particles being down, or one up and the other down, or the first down and the other up. Yes. Yes, Ali.
So when if we measure only one particle, not the other one, then can we see that the other particle would be opposite of this one?
That is what quantum mechanics would predict, because of the intrinsic entanglement.
But like we haven't done any experiment on that one, right? So this one has collapsed into one of the eigenstate.
Yeah.
But can we say that the other one has also collapsed into?
Yeah, that is the instantaneous information which is shared between the two particles. That is precisely the statement of entanglement.
But like there has been no experiment on that one, right?
Huh?
Like, there has been no experiment of measurement on that one, right? Like we just measure one particle on this side.
Yeah, but how do you verify this? You cannot verify this unless you carry out a measurement. So, you have to carry out a measurement, and when you do carry out that measurement, then the result will be exactly this, that if this particle is up and if those magnetic fields are exactly parallel, then it will be exactly down. So, if you have not carried out a measurement, you do not talk about it. And this is to some extent, it goes back to the question, is the moon there if nobody is looking at it, all right. If you are not looking at it, do not talk about it, you talk about what you observe. Okay, means about what may exist or what may not exist is not for us to discuss. We talk about what are the results of our observations, and do we have a theory which accounts for this. So, quantum mechanics gives you an account of what we observe, and it gives us an accurate description of what we observe in nature, to which no experiment has been found to violate. So, we have got a model which describes nature correctly, and we do not discuss parameters which have not been measured. That is not in the purview of our discussion. And Niels Bohr said at one point that quantum mechanics will not answer all the questions, but quantum mechanics will tell you what are the right questions to be asked. So, if you are not carrying out that measurement, there is no point talking about it.
So have we done any experiment where one of the measurement, like both the measurements are done at like some time difference? Like first we carry out a measurement for one particle, then after some time we carry out the measurement for the other particle.
These have been carried out. Yeah, these have been carried out. As a matter of fact, I discussed this in terms of the Young's double slit experiment, and the interference takes place because the photon or the electron or whatever is interfering with itself has the possibility of having two alternative paths. That is when you see the interference. And if you have any marker, any way of determining whether it has gone from slit 1 or from slit 2, and these markers can be of various different nature, and I discussed some of them in an earlier discussion, then the interference is lost. Even if the result of the experiment due to the marker is done much later by when the particle would have reached the detector, even if it is done much later. If there is a provision to have a marker, then the interference is lost.